Hello Beanie fans and welcome. In today's episode we have a comparison between angular contact bearings and radial bearings or cartridge bearings. Well, they're actually one and the same, and we're going to come to that shortly. Now, last year I was fortunate to be invited onto the GCN show with John Cannings, and some of the questions at the bottom of this video revolved around angular contact bearings and how they worked and what they were and all that kind of good stuff. So today we're going to learn about that, and then you can make your own assumptions and conclusions and draw from that what you will. Now, before we can go any further, I need to explain to you about two types of bearing loading characteristics. The first is a radial type and the other one is an axial type. To give you an illustration, I've got my bike here. I'm just going to lift it up and then show you. Just for a note, make sure when you lift your bike the pedal doesn't just whack your balls like it did then. Anyway, right, so this is my bike and you can see the wheels, steering, all that kind of stuff. If I just talk around some of the areas where you get axial loads first, the most predominant one is the headset. So this is the best example of an axial bearing on the bike. So headset bearings are predominantly biased towards axial loading, but they also have an element of radial loading. Radial loading is turning, so that is the wheel is taking a radial load by spinning, but if you are cornering and you apply a sideways load, that is an axial load on the bearings. So if we just go from front to back, the front wheel is biased towards radial loading, but there's also a bit of axial loading when you go around a bend. The headset is predominantly axial. The bearings in there will never do one revolution in their entire lifetime. So they are designed for an axial load, which is basically into the bearing. The bottom bracket, again, if I was to turn the bike through, it won't fit. If I was to turn back, I don't know if that'll show up. The loading that you apply to the pedal gets bent through, so the bottom bracket is quite heavily loaded. So you've got a radial load and an axial load acting together. Then as we go towards the rest of the bike, the back of the bike, the pulley wheels, they are predominantly radial load. There's not really much axial load until you change gear. At the point where you're changing gear, there's a lot of axial load. Once it's engaged and the chain has moved to the next set of teeth, the axial load is diminished and you are still in radial mode. Now, in terms of who uses what, the vast majority of bicycle components in wheels and bottom brackets and all that kind of thing use radially biased bearings, so deep groove ball bearings. The exception is Shimano. Shimano wheels, like this one, use angular contact bearings. So an angular contact bearing in the bicycle world is sometimes called a cup and cone bearing. And we're going to come to that in a minute, but Shimano and Campag, they are really the last users of cup and cone bearings. Everyone else has moved to Cartridge or what's known as 6000 series bearings. So what we've got here is we've got a BB30 bearing, which is a 6806 or 61806 bearing, and they are the same size. This one's an NTM bearing. Really, for the purposes of this video, this bearing is too small and I can't really show you the features on that. So what I've done is I've got a bigger bearing. And this bigger bearing is the same type. It's a 6000 series bearing, but it's just bigger, so I'm using that for photographic purposes. This one's used, and the technical term for that bearing is fucked. The main reason for this is it's just old, and well, what we're going to do is we're going to cut it up in a second. Over here we've got some angular contact bearings. So these are headset bearings from Cane Creek. Again, these are too small for photographic purposes, so what I've got is I've got a big bearing from Fag. So Fag kindly donated this bearing to me because they thought it would be a good educational snippet for this video. This is essentially the same as what's in there, but it's bigger. But the reference geometry and all that kind of stuff, which we'll go through, is the same. So just to give you a quick overview of some of the terminology that we go through. So if I use the smaller bearing, just to start off with, this black thing is the seal. Seals come in generally 3 types. So there's this one, which has no seal. This one, which is a non-contact seal, so it spins quite well. And the next type is a full contact seal, so the black bit touches both the inner and the outer. If I go back to this bearing, people talk about races, so this bit here is the outer race, this bit here is the inner race, and this bit in here is the cage. Now all of these things move at different speeds, so what I'm going to do now is I'm going to get a black pen and just mark it so I can show you. I couldn't find a black pen, so I've used green dots. So we've got a green dot on the outer race, this one won't move, green dot on the cage, and a green dot on the inner race. If I start spinning the inner race around, you can see that the inner race is 180 degrees from where we started, but the cage has only moved sort of to the 2 o'clock position. So he's always playing catch up. At this point, there, where the mark's just rubbed off, that's where it caught up. I'm just going to mark it again. And this process carries on. So we've got the inner and the outer lined up again, and the cage is off to the side. They'll all come back to meet at a certain point, and they are called fault frequencies. Now one of the things about bearings is all of them, all the decent ones, are hardened. So if we get the fucked bearing and then a screwdriver and try to mark it, it's almost like it's running on glass. It won't even touch it. So when you put that bearing into a bike frame, you need to make sure that it doesn't move about, because if it starts to move about and wobble, it will totally trash the bike frame. Just before we chop this up, this is what you probably regard as the back of the bearing. You can see the geometry difference. So if I just flip this around, on this side, the outer race is quite wide and the inner race is quite thin. If I flip it around, we've got a very wide outer race, and a very wide inner race, and a very thin outer race. So when we chop this bearing up, we'll have asymmetry, whereas the 6000 series bearing is completely symmetrical. So I've just finished now. Make sure that doesn't happen to your angle grinder disc. So what I've just done, don't try at home, you run the risk of dying. So the bearings have been cut up, and what you should be able to see is the difference between deep groove ball bearing, or cartridge bearing, radial bearing, which is the one on the left, and an angular contact bearing, or some people call these cup and cone. This isn't actually a cup and cone bearing, on the right. First thing to notice is the deep groove ball bearing is symmetrical. So if you look at this might seem like an optical illusion as to though this isn't symmetrical, and that's mainly because I haven't cut it completely straight, but that is symmetrical through that axis. The angular contact bearing is clearly asymmetrical, so you've got a huge lip on this side, nothing on this side, huge lip on this side, nothing on this side. You can also clearly see the metal cage, so the brass metal cage, whereas on this one you've got this pressed riveted cage. This angular contact bearing can only take load in one direction, so it can only take load that way, so you have to preload it that way. The contact angle is part of the geometry of the bearing, and it is where the ball touches the inner and outer race. So in this case it'll be around here on the inner race and around here on the outer race, and that angle is fairly biased towards the axial direction. If you do the same thing with the Deep Groove ball bearing, the contact angle is much, much shallower, so it's contacting here and here, but it will take load in both directions, so its contact angle looks a lot more like that in terms of the pencil mark. So I've done a few slides and things so you get your head around this. If I press the right button. Right, so angular contact bearings against radial ball bearings. For angular contact, you could read cup and cone bearings. Bearing basics, right, there are two loads in a bearing. So if we got the chopped up bearing, which I have here, radial load, which is the turning load, and then the axial load, which is pushing down. Now if you were to draw them out, what you would end up with is something that looked a bit like this. So we have the radial load, which is acting on the outside, where's the pointer, and the axial load, which is acting in that direction. And if you combine the loads, you've got this, so you've got a sort of diagonal load, and that's what happens most of the time. So if you think of a practical example, and let me pick the SolidWorks file, so let me do that. Just try that. So this is a wheel that I've drawn out. So you've got the hub, spokes, rim, tyre, tube, all that kind of good stuff. If we were to take a cut through this, so let's do that like that, and then zoom in. So through the center of the wheel, this is the front wheel, you've got two bearings, one either side, and the shaft that it rotates on. Now if you were to depict that back into mathematical terms, what you would get is something that looks like this. So there's your two bearings. There's the force, so that effectively is the force that's comes from the spokes, and then you've got a radial load and an axial load. So the blue is the combined load, and the radial load and the axial load are there and there. The difference is the difference between angular contact and radial, and it may not be clear on your picture unless you zoom in, is like this. So this is your angular contact, and this is your radial. So what you can see is the angle of this blue line or blue arrow is much steeper in this case. Now angles for bearings are actually measured from the vertical. So when you measure it from the vertical, you would say that angle was actually shallower. In this case, the angle is more obtuse, if that's the right word. So it's heading more towards horizontal than this one. If you look at the internal bearing geometry, there is a contact point. So the ball in each of the bearings touches on the inner race, which if you've got a cup and cone bearing, the inner race is the cone and the outer race is the cup. It touches at a point, and so you get a Hertzian stress built up there and there. That angle that it generates is called the beta angle, and the key difference between those is the size between a radial bearing and angular contact bearing or cup and cone bearing is the size of that angle. So a radial bearing has a much smaller contact angle, so it's radially biased, which is why it's called a radially or deep groove ball radial bearing. Generally, angular contact bearings have bigger balls, so for a size they usually have bigger balls. If you were to compare the difference between an angular contact bearing and a radial bearing, you've got that, which is my phone, you've got that which is the angular contact angle versus that which is a radial contact angle. So it's much shallower or heading more towards vertical. To give you a summary of differences, so we've got on the left angular contact, they are asymmetrical in section. So if I was to show you that, let me show you with this SolidWorks file. This is a cut through of an angular contact bearing. So if you look, and I've showed you in the cutout section of the video where we went and angle grinded through a bearing, you've got asymmetry. So if you were to draw a line straight through, a vertical line, the right hand side and the left hand side are not the same. So this bearing will only take load in that direction, in that diagonal direction. Whereas if you look at a 6000 series bearing, that is symmetrical straight through the middle. So you can use that in either direction, but the 7000 series or the angular contact bearing you can only use in one direction, so which is in that way. So you would have to, if you pushed on the inner race, you'll be pushing from right to left. Going back to this presentation, just set that. You can only take the load in one direction. In the other direction, it's doing nothing. It's got good axial load capability, and that's because the contact angle is heading more towards the axial direction. But it has high radial friction, so if you want to go fast, then that's not really suitable, basically on wheels. And then the big advantage, and don't let anyone kid you otherwise, is if you've got a cup and cone bearing, you can have very slack, and I mean very slack, manufacturing tolerances. Because you've got a preload system to take up the slack. So it basically, if you're the likes of Shimano, it is cheap to make because you've got the economies of scale where you can make the bearing surfaces in-house. You don't have to buy bearings in, so it is cheap to make, and there's no arguments about it. Other thing is, right, we're going on to the radial bearings, the deep groove bearings. They are symmetrical, so you can use them in either direction, doesn't matter which way you put them in. Can take load in both directions, but it has a limited axial load capability, so you wouldn't really want to use these for something like your headset. They would be rubbish for your headset. But they have very low radial friction, so if you want to spin fast or in a time trial with wheels, then these bearings will get you there faster. Now, some people have asked, how do I convert from a radial bearing to an angular contact bearing? You probably want to get some engineering input before you do this, but if you just want to give it a go anyway, this will explain how. It is not suitable for, this conversion is not suitable for all types of bearing arrangement. So if you've got a fixed floating arrangement, so SRAM GXP bottom brackets or Praxis M30 bottom brackets, forget it, because you're wasting your time. It's not going to work. But you can, if for example want to use BB30, which is a popular BB30 or BB386 Evo, all of this lot, PF30, they will allow you to do this. So you can fit angular contact bearings in there. To give you an example, so I'm going to pick BB30. BB30 bearings are 6806. That's the number that's on the side of them. And if you've got an SKF bearing, you'll have an extra 1 in range of options pen, right? You'll have a 1 in there. But if you've got anything Japanese, so NSK or MTN, it'll just be 6806. Those numbers translate to bore size. So the bore size are the last 2 digits. If you go 06 times 5, 6 times 5 gives you 30 mil, and that is the bore size. The outside diameter is 8. So there's a sequence that starts at 7. So 7 is the thinnest bearing. Then it goes 8, 9, 0, 1, 2, and so on. So an O series is actually bigger outside, beefier than an 8. And then the final one is the 6. So a bearing type 6 is deep groove radial bearing, and a 7 will be angular contact bearing. So if you want to fit angular contact bearings in your BB30 bike, all you do is change the first digit to a 7. And that's it. So you just literally the same, the rest of the dimensions of the bearing are the same. It's only the first digit that needs to be changed. Now this is a slide that you probably want to think about. So which is better? Well, it is totally dependent on the application. So in certain areas where there are high axial loads, headsets, pedals, you want an angular contact bearing in there or an axial bearing, because it's not suitable for a deep groove ball bearing. Angular contact bearings are poor when items are lightly loaded, so things like pulley wheels is the only example I could think of in my head. Those kind of things, not worth it. And one thing that the angular contact bearings have is quite poor sealing. They don't seal well because there's a lot more movement in them. So you'll gain in the sense that they have a higher load rating, but then you'll lose because you will have to service them more. And just a bit of an aside there, but I've put NTN do not make small sized angular contact bearings for that very reason, with seals. And I don't think FAG do, and I don't think SKF do, but I didn't ask them. Yeah, and then size for size, an angular contact bearing will have more friction because of this contact angle and the preload requirements. To overcome the contact angle, you'll get more friction in there. There is a considerable overlap between applications, so wheels, bottom brackets and things, you could use angular contact or deep groove, depending on what you want. I mean, Shimano wheels have historically always been cup and cone or angular contact, and they do last well, but you need to service them. The pedals, so I've got a set of Dura-Ace pedals, they have an angular contact cup and cone bearing and a roller bearing in there. Their Ultegra level pedals have a slightly different bearing arrangement, and I think it's mainly to do with weight. So their bearing arrangement is slightly different, but it's geared more towards I guess cost saving more than anything else. The thing you really need to consider is bearings are like tyres, they will wear out, so get ones that you can replace easily. Cup and cone bearings, so the ones on Shimano wheels, they are not easily serviceable. Very rarely will the balls fail. It's usually the bearing surfaces, so the inner race, which is the cone, and the outer race, which is the cup, they will fail way before the balls fail. And while I'm on it, one of the questions that one of the viewers asked was, why do some bearings have a retainer on them, or the cage? The cage is there to stop the balls hitting each other. The balls are not all exactly the same diameter, and because they're not exactly the same diameter, they will travel along the inner race or the outer race, however you want to look at it, at a different speed, so they'll hit each other. The cage is there to keep them equally spaced, so if you don't have the cage, they will touch at some point. That's it. I really hope you enjoyed this presentation. If you've got any questions, then use the comment box below or send me an email. I do read all of the comments. I don't respond to all of them, but I do try to. If you've got any other suggestions or things, then whack it in the box there. And remember to whack that like button and subscribe button if you thought this was good. If you didn't think it was good, then hit the dislike button. If you want to have someone else on the board of engineering fuckwittism, then by all means get in touch. Thanks very much, and until next time.